there, my name is Dennis Mulder and I'm the VP of Customer Success at Volumez. At Volumez, we specialize in providing cutting-edge data infrastructure as a service that's designed to meet the needs of modern enterprises. Today, I'm excited to share with you the latest benchmark results from our execution of the MLCommons MLPerf Storage suite. This benchmark is crucial for evaluating the performance of storage systems, in supplying training data during model training. By focusing on key metrics such as latency and throughput, the MLPerf storage benchmark helps organizations optimize their data infrastructure, ensuring faster and more reliable AI model training. By selecting the right storage platform, companies can further optimize the utilization of expensive GPUs. Volumez is a new architecture for block and file storage in the cloud. Volumez separates the storage control plane hosted in the Volumez cloud from the storage data plane, which runs in the customer virtual private cloud and in the cloud data center. Volumez is a composable infrastructure software that makes it easy for developers to request storage resources, similar to the way they request CPU and memory resources in Kubernetes. FileDirect is our AI composable data infrastructure solution designed to support large-scale training jobs, which is the topic of today. FileDirect allows hundreds of GPUs to read simultaneously from the same volume and the same dataset. It's also possible for a single writer to prepare the next generation of the dataset or prepare for the next experiment while the training job is running without affecting it. With Volumez, we've provisioned an environment in AWS, which we want to check out now. So let's look into this slide, which outlines the configuration we have set up for MLPerf. So using the Volumez control plane, we've provisioned 137 host nodes, C5N, 18 extra large and EC2, each running 3 H100 accelerators for the Unit 3D workload, as defined in MLPerf. We also provisioned 128 media nodes of type i3E and 24 extra large, each with 60 terabyte NVMe drives per node. These have been used to create the volumes we need for MLPerf. In addition, we have one C6IN32 extra large EC2 instance for the data generation. We created two volumes, a data volume size to 350 terabyte using our performance optimized policy, which does not do any erasure coding or compression, and one checkpoint volume size to 100 gigabyte, which is also using the performance optimized policy. In the benchmark that I'm showing you here, or the benchmark configuration that I'm showing you here, we made two changes to the benchmark, which are compliant with the rules set in MLPerf by MLCommons. The first change is in how we load the data. Our custom data loader issues ODirect IOs to the storage system. This allows the IOs to be issued to the storage directly without passing through the OS page cache, which would create redundant CPU bottleneck and memory pressure. The second change we made is in the data format we used. The data was generated in MPY format instead of the MPZ format. The difference between the format types, obviously, is that MPZ represents compressed tensors, while MPY does not compress the data. The decompression of the MPZ files is compute intensive. Hence, it would prevent the benchmark from scaling and achieving the required arithmetic unit utilization, although the storage can in fact keep up. In a separate submission, we also made another change in the barrier frequency. This is outside of the scope of the results I'm showing you here in this video, but to summarize, we explored various methods to address communication bottlenecks in distributed learning, communication between nodes, such as asynchronous training and gradient compression. We ran experiments to observe the impact of changing the barrier interval and communication frequency and storage performance. The results were slightly better, but if you want to learn more about this change and the surrounding commenting around networking and the actual use cases, feel free to connect with us and we're happy to further elaborate. So with that, I'm sure you're curious about the results. Let's move into our results. So we literally believe we have shattered the MLPerf benchmark. We're showcasing the superiority of our cloud data infrastructure with FileDirect. We basically achieved an impressive aggregated throughput of 1.075 terabytes per second, almost 1.1 terabyte per second, maintaining an average 92.2% AU utilization as measured by the benchmark, the equivalent basically of GPU utilization. The Volumez monitoring system recorded a consistent peak performance rate of 1.25 terabyte per second, which we'll demonstrate shortly in the accompanying video and dashboard. The discrepancy between those numbers that I talked about arise from the benchmark measuring throughput over the entire duration, including periods where between epochs storage is not fully utilized. And we'll see that in the numbers. Throughout the benchmark, we observed nearly 10 million IOPS per second, right? So input-output operations per second. We're thrilled with these results and are eager to know if you have workloads that could benefit from this level of performance. Now, let's switch to a video that we recorded during the actual benchmark back in August, July, August, where I will guide you through a run of the benchmark, as well as fast forward the specific sections for brevity's sake. Following that, I will also showcase our monitoring system, and we'll go back in time in the browser to highlight key areas of interest in the results. So what we're seeing here is basically the startup of the next run. On top you see the read bandwidth and read IOPS in our monitoring portal, where you actually see the previous runs, right? You see 5 epochs, basically 5 hills before this run. And we're now going up and starting that first epoch. On the left, you see actually us collecting our telemetry. On the right, you see top, which monitors the NVMe over TCP processes going and running across all the nodes. What I want you to pay attention to is actually the memory usage, as well as the buffer cache. You see that during the run, especially at the peak, it stays very static. Basically, this proves that we're reading all data from disk and not doing tricks within memory caching, which is actually impossible because of the randomness of the workload. So with that, let's zoom out again and I do a little fast forward so that we can look towards the end of the video, how it's running. Apologies, by the way, for the video quality. During the runs, we didn't properly record the actual run. So I'll also dive deeper into our actual portal, a monitoring portal separately. So let's zoom back out. And here you actually see your then go through the rest of our monitoring portal. I'll show you the portal separately, but briefly, right, you see queue depths, read latency, write latency. Well, there's no writes. The media reads, and I suggest from here onwards we put it on 10 times the speed, no, actually 16 times the speed, so that we can see our hills being built across all the epochs, and then proceed and finish the actual workload, so that I briefly described what you've seen. So that's the third epoch completed. Every time you see the quick slowdown, we're hitting peaks again. Complete the fourth epoch, and we're starting the fifth. And with that, the workload has concluded, and we see you then collect the data points. As you can see, multiple runs have been made already. We collect our data in JSON and then do our aggregation in the results. I hope this was helpful. Let's dig a little bit deeper into the portal. So let me show you the Grafana portal. Back on the 13th of August, for the people that paid attention, yes, we're 1 hour off. This has to do with time zone differences in Tel Aviv and Amsterdam, where I live. We see the physical capacity, 350 terabyte that I talked about before, the same as the provisioned capacity. We didn't do any thin provisioning, so these are then the same. With our other features, you would see different graphs, so to say. And well, we'll see the read bandwidth here close to 1.25 terabyte, 1.1 on average, and the read IOPS going close to 10 million IOPS. And we have these capabilities to, of course, dig deeper and view the details here, filtering capabilities, etc. This is our monitoring portal that you get access to if you are using volumes. And I'm looking at the data volume, right? We have all kind of other ways to slice and dice the data. Data that we do collect are read and write bandwidth, read and write IOPS, read and write IO size, and latencies. We see latency, by the way, peak occasionally. That's exactly at the moment when the transition happens between the epochs, as I've explained before. This is the nature of how MLPerf is set up. And here below we have queue depths and even the data per media device that you can actually look at. With that, I'm going to close out this video. I hope these data points and this performance intrigues you as much as it does us. Again, if you have workloads that could benefit from this, feel free to reach out. We can talk more about our testing, about the architecture of volumes, and of course talk about your workload and how we can make you successful with volumes. Thanks for watching the whole video till the end, and I hope we meet again soon.